Hello, I am Tom Choi. Thank you for coming to watch my presentation. I will introduce the paper Autoencoding Variational Base, which is also known as the Variational Autoencoder. These are the topics we'll cover. The Variational Autoencoder is a latent variable model. So I'll start with an introduction to latent variable models, and I'll talk about an issue and how to solve it. The approach is to use variational inference and optimize elbow. Next, I'll talk about the paper. The variational autoencoder also optimizes elbow. In contrast to variational inference, this does not make any assumptions. And while optimizing elbow, some problems arise. So I'll show you how to solve it. This is the main part of this presentation. And lastly, I'll show you the code in PyTorch. A latent variable model assumes that there are hidden or unobserved variables in a given X. We call such variables latent variables. As I mentioned earlier, variational autoencoder is a latent variable model. This is how to construct the model. We can represent the model as P of z given X, and we can transform this to this equation at the bottom. If it's possible to calculate this, our work will be done. But there's a problem. The problem is that computing integrals is quite difficult. In most cases, integration is impossible. And even it's possible, when latent variable z is high dimensional, it requires too much resources to compute. When direct computing is difficult, approximate methods are quite useful. The variational inference is a method for approximating one distribution to another. Now, I'll talk about KL divergence and evidence lower bound and set our goal. The KL divergence is used to measure the difference between two distributions. It has some properties. The first is that it's asymmetric, and the second is that it's always greater than or equal to 0. When the KL divergence is 0, it means that there's no difference. So our goal is to minimize KL divergence. If the KL divergence is close to 0, then we'll obtain the distribution that is almost the same as the real one. I would like to tell you something in advance. The goal of minimizing KL divergence is equivalent to maximizing elbow. This slide says what the elbow is. This P of x is called evidence in Bayes' rule. We can transform this to the equation on the second line, and by using Jensen's inequality, we can change the equality sign to inequality sign. Therefore, we can get the lower bound of the log evidence. We call this elbow. Now, I'll show you how minimizing KL divergence is equivalent to maximizing elbow. This is the definition of KL divergence. This can be written as a log P of x minus elbow. The log P of x is a constant because the x is given, so we can remove this. And now we can notice that if we maximize the elbow, then the KL divergence will be minimized. As the elbow increases, the difference will be decreased. The difference is the KL divergence. Now that we set our objective, I would like to introduce variational inference and its optimization. Variational inference assumes that the latent variables are independent. The Q of Z is the same as the joint distribution of latent variables and can be written as the product of distributions. Under the assumption, we can rewrite the elbow in the form of the equation at the bottom. I'd like to remind you that we would like to find the distribution QZ, which is similar to the real one. To achieve this, we need to maximize elbow. The first term will be removed because it is not related to QZ. And I will notate something that is not J as minus J. Then Q minus J are not related to QJ, so the sigma will be removed. And using the definition of expectation, we can rewrite the equation like this. To find the maximum elbow, we differentiate elbow with respect to QZ. We can use Lagrange multiplier and calculus of variational. To achieve a local maximum, the last equation is required. So we can differentiate like this. Q partial Qj times expectation Q minus J partial Qj is just expectation Q minus J and partial Qj log Qj partial Qj is log Qj plus Qj times inverse of Qj. This is gonna be log Qj plus 1. And the last term will be just lambda. And we can take exponential on the both sides and remove constants. Then we can get the Qj maximizing elbow. This is an algorithm for updating elbow. Until elbow has converged, we perform this. We For each variable, we set qt to this equation, which is that we just obtained, and keep others fixed, and then compute the elbow. This is just the definition of elbow. This slide summarizes the background. First, we want to get the latent variable model, but we couldn't calculate the exact distribution due to intractability. So we decided to approximate a distribution to the real one, and we found that by maximizing elbow, we can minimize the KL divergence. I also introduced the assumption in variational inference, which assumes that latent variables are independent. Finally, I demonstrated the method for obtaining QZ that maximizes the elbow and updating the parameters.